let's
Take a nap.
take a nap. Yeah. Let's pick back up really briefly with transmission lines. Remember, we talked about the fact that we need to know a couple different things about transmission lines. Number one is what?
The characteristic impedance.
There we go. It would be the characteristic impedance. Why is the characteristic impedance important? Why does it matter?
We talked about like when you're linking two things up.
Okay. Yeah, if you're putting a load on it or linking another. Yep. If you're linking a load to it or linking up two cables, you need to match the characteristic impedance, because only when they're equal do you get maximum power transfer. Otherwise, you get reflections, and if you get reflections, then you get this VL over VR. If this thing gets much above 0, it looks like noise back along the line, because it's just a reversed copy going the other way. So you want to minimize this. And then we talked about VSWR, the voltage standing wave ratio, which was, does anybody remember? 1 plus the absolute value of reflectivity over 1 minus the absolute value of reflectivity. So if you know either VSWR or the reflectivity, that gives you a measure of how much of your voltage is bouncing off the end. What do you want VSWR to be, ideally? 1. Yep. Or as close to 1 as possible. Then the other thing is, we can find the impedance at any point along the line by using this equation, which just has the characteristic impedance, the load impedance, and then beta and x. X is our position along the line. Does anybody remember what beta is?
Real?
Beta was, if we go back here a couple slides.
Oh, bandwidth, but apparently not.
No, bandwidth is B. There we go. Gamma equals A plus J beta. It's the phase shift, but here we go. 2 pi over lambda. Right? Okay. So we figured out you can do that with all the equations. Then you can also use our favorite method, the Smith chart. Okay? Smith chart, using the Smith chart is relatively straightforward. I don't know about easy, but there's... confusing? It is somewhat confusing. Okay. Main thing, what's that? You need to come up with one. You know, you could have like a kidney-shaped chart. It worked for pools, right? We went from square pools to round pools to kidney-shaped pools. Make some sort of kidney-shaped chart. That'd be cool. Okay, the steps in a using the Smith chart is mark your ZL over Z naught fraction. So in this case, this is ZL equals 1/2 Z naught. Mark that along the real axis, which is the line down the middle. Draw a circle around the center that passes through that point. Where it crosses the real axis on the right side, that's the VSWR. Then, once you've got that, remember that around the outside here, this is distance away from the load up to 1/2 a wavelength is one circle around. So at any point away from the load, we can draw a line, like if we want to say 0.2 wavelengths away from the load, we can draw a line from there straight to the center, and where those cross is the impedance at that distance from the load. So what would the impedance here be? Well, it looks to me like it would be about 1.6. plus j 0.7 or so, right? It's hard to tell on this chart because there aren't enough lines on it, but remember, you curve down to the real axis following the lines, and then you curve out to the imaginary axis around the outside. Does everybody remember that stuff? Okay, let's do one more. We had a couple example points that you could look at. We talked about. We did an example where ZL equals 0.5 Z naught. For example, if we split it and okay, here we go. All right. Then next thing, we didn't really talk about this. We talked about the VSWR, the voltage standing wave ratio, but we didn't talk about development of standing waves. And because we've already got something tied to the fan today, I'm not going to break out the fiber optic cable and show you standing waves. But does everybody know what standing waves are? Yeah, you can set that up with acoustic waves pretty easily. But what is a standing wave? I mean, we already said we've got waves traveling down, and then we've got a wave traveling back the other way, right?
Is that where it kind of reaches like a status quo, staying the same? Like if you were to pull it up on the
Yeah.
oscillator, it
Okay.
stays the same instead of shifting left and right.
Right. Well, actually, tell you what. Let's do this.
It's like a Ryan will hold it for you.
All right. Take one into this.
Thanks.
Tie it to your belt.
Appreciate it.
Okay, now we'll do this kind of short. Theoretically, I should be able. Now you saw already. I can make a wave travel down and bounce back, right? So you can too. So, but now watch this. If I get this going, okay. Whoops! There, I had it for just a second. There we got standing waves for just a second. Did you see? There we go. Oh. No,
You
they're
have to
not.
get that perfect frequency.
Yeah, I got it. There's standing waves. It does have a circular component to it, but that's set up standing waves where we have peaks. We have 3 peaks and then 2 nulls in there, right? Okay, so that's standing waves. Yeah. I'm just glad that John Overton from General Dynamics didn't walk by right then. He walked by a couple minutes ago. Thanks.
And then we've been going.
No, he wouldn't have. He would have been. He actually wanted to send one of his people to sit in here. Was disappointed they didn't get a chance. So, what? Just to sit in on this class, and be a spare student, I guess. I don't know. Okay, so as long as the phases match up, if we have an in-phase reflection, what happens is we've got a wave going this way, a wave going this way. They match up, and you set up standing waves. If the length is just right, it'll set up standing waves like this, right? Which is what we just saw there, where you have a null that holds still, and peaks that more or less hold still. This is just a way to look at it. We're not going to go through this in a whole lot of detail because, well, we've got other stuff to cover. This is a whole interesting thing in and of itself, is looking at how standing waves work on the wire, and you actually get weird effects like the nulls don't heat up as much as the peaks, so your wire expands at different rates in different spots, and you get all sorts of weird effects. How many of you have ever put a CD in the microwave? Like half the class.
Is it cool?
It is cool. Okay, if you put a CD in the microwave, in the first like 1 second or 2 seconds, it does like this cool lightning storm over it, just like But then if you leave it in there for a second, and I would suggest putting it on a paper towel and having a well-ventilated room, if you do this, you get hot spots, and it looks like a planetarium kind of, little stars all over it, where the peaks of the standing waves, microwave standing waves, focus on particular spots around on the CD and burns up. I mean, they make little tiny red hot melted spots, just dots here and there.
No.
We could.
No.
How about we could do that at lunch or on break? But
But Han Solo I put in there. And get him out of the car plane.
Nice. Okay, that's standing waves. So just a couple of things that happen if your standing waves get to where you've got peaks just at the wrong spots. It can occasionally cause, and not all that often, but it will occasionally cause physical issues because it'll expand your wires at spots where there's not that capability to do it. Okay, so here's the regular picture of it. The voltage, where the voltage goes to 0, the current is max. Where the voltage is max, the current goes to 0. And so you end up with this current curve that looks like this, and a voltage curve that's just exactly opposite, right? Because it goes to 0, then it's max when the current is 0, and so forth. So a quarter wavelength here for an open circuit. You notice the voltage is at the peak at the end because it's an open circuit, right? You have to have a peak voltage right at the end of the line. Does that make sense to everybody? Why not? Why would you have to have a peak voltage at the end of the line in an open circuit? Right, there's no current flowing there because there's no place for the current to flow. It's an open circuit. So your voltage has to be maximum because I equals V over R. I is 0, so V has to be max.
I mean, I see that, but at the same time, if resistance is infinite, then see what I mean? It wouldn't matter if V is minimum or max. It's still going to be relatively close to 0.
Yeah, well, true, but when you've got no current flowing, it's like it's like in your tap. Let's go back to our water analogy. If you turn the faucet off, the pressure at the faucet is equal to your maximum pressure, right? Same thing with current or voltage. When you have an open circuit, voltage is maximum. Closed circuit, obviously your current is going to be maximum. Your voltage is going to be 0 because there's nothing for it to generate a voltage across since it's a closed circuit. So we end up with standing waves that look like this for a closed circuit, standing waves that look like this for an open circuit. This to me seems like something that's a little bit hard to comprehend. You would think, because we learned this with DC, and with DC and open circuit, there's no current anywhere, right? Current is just 0, voltage is max. But in a transmission line, we actually slosh current back and forth within the line itself. So there are spots where the current is maximum and where the current is 0. And that's how these standing waves end up getting set up. There's an example in your book. We're not going to cover it, but example 12-6 in your book shows how standing waves get set up. And we'll actually come back to this one when we talk about antennas. So that's pretty much, yeah, I just threw a few Smith charts for possible examples. If you want to look at those in your book, feel free, but we're not going to go through them very much. But other thing, transmission line section equivalency. If we have a transmission line that's a closed circuit that ends right at the end of a wavelength, then it looks like an inductor and capacitor in parallel. An open circuit that ends right at the end of a wavelength looks like an inductor and capacitor in series. And at resonant frequency. Okay? If we have a closed circuit that ends too short, then it's inductive. An open circuit that ends too short is capacitive. Conversely, a closed circuit that's too long is capacitive, and an open circuit that's too long is inductive. Well, longer than a quarter of a wavelength.
This is the actual length of the wire.
This is the actual length of the wire. It can have however many wavelengths back here, but if it doesn't end on a multiple of a quarter wavelength, if it does, then it's going to look like a resonant circuit. Okay? If it does not, it's going to be either inductive or capacitive based on the length. And so what we want to do, okay, the big question here is, so what? Right?
It seems like I have to cut every cable I make, and it says like I should know the wavelength.
Okay, yeah, technically you should.
Oh, okay.
If you're making an antenna and then you like, for example, it's crazy. We have a physical example right here. Okay, so here's an antenna. It's got a cable that starts right there and connects it to that machine right there. Connects it over here to your radio. That cable, to get maximum power transfer, should be a specific length, and it should be a multiple of a quarter wavelength of the exact frequency you want to use it with. Now, there's some problems with that. Number one is you don't just use one frequency all the time, right? There's more than one frequency. So when you change frequencies, then what happens? Yeah, you change that. Exactly. If I want to change, and I don't know, don't you guys do that? If you change the radio station in your car, you go cut the cable and move it just a little bit?
I don't know.
I don't know, infinite number. A lot.
It's like the old radio, your SINGARs in the back. You used to have to get just the antenna dial on the bottom.
Yeah, okay.
A while back, because it was cut to like 4 frequency bands.
Yep. Okay, so
Yeah, the other one here, that's it, automatically tuning to whatever frequency.
right, and Captain Sherburne's got a little antenna tuner, which he procured at great difficulty despite an eBay sniper, right? Which takes care of that by reading what the frequency of the radio is set on, and then tuning. We haven't talked about this for antennas, but it's the same thing for the antenna. Tuning the cable antenna whole thing by adding. Now here's why it's important. If it's too short and we're ending with a closed circuit, it's going to look inductive. So what we have to do is just add capacitive value to it till it appears even, right? So
oh, sorry.
no, go ahead.
Stuff inside there that's
So there's stuff inside there that adds in capacitance, basically, to make it to tune it back in place.
Common denominator wavelength and then have the cable rack. So.
Well, if there's just one frequency you're using, yeah, you make your antenna exactly the right length. Weirdly, the antenna, and we'll talk about this more in wireless, but the antenna is going to be a different length for a quarter wavelength than the same frequency, at the same frequency than the wire is going to be for a quarter length. Anybody know why that would be the case?
Honestly, can you say it again? So I couldn't.
I'm sorry.
Say it again.
So quarter frequency wavelength line antenna meant difference. All right. If you have an antenna, let's just for the sake of simplicity, you have a quarter wave antenna at a particular frequency, and you have a cable that you want to be a quarter wavelength long. Those two things won't be the same length. Anybody know why? Not quite. There's one reason, and it's because of the difference between air and cable. What's different in air and copper? not so much the
That's what I said,
insulation.
impedance, so that's why we didn't say that.
No, not impedance.
It's the same.
Not resistance. It just doesn't matter, actually. Okay, what we've talked about this in class. What is a difference between free space and copper about electromagnetic transmission? How fast, right? The velocity is different. In free space, the velocity is the speed of light. In copper, it's maybe a third of that. So a wavelength in copper, remember wavelength is what? Velocity over the frequency, right? So if the velocity goes down, our wavelength goes down. So wavelength in the cable connecting your antenna is different than the wavelength in the air itself. And that's gonna we'll see more of that stuff when we get into wireless. Right now we're just talking about the wire, not really talking about the antenna. But yeah, we can tune it then by adding capacitance. And there's a bunch of ways to do that. There are quarter wave matching stubs, there are balun, there are all sorts of things, but again, we'll talk more about that once we get to antennas. Okay, so that is the end of the section 2 slides. I mean, we're...
What? We're not done. What?
Yeah, that was just catch up from yesterday.
Yeah, now that was cleaning up yesterday's stuff. Okay. And whoops. Dang it. Oh, there we go. All right. I don't know why this does this, but okay. Where did that go? Let's try this one more time. There we go.
Full disregard.
Cat and dogs. This big cable has been sitting here for a while.
All right, let's take a look at where all this stuff fits. So we have a source. Right now we added I'm not going to draw all these boxes in on the back end, but so far we have a source, channel, sink. In the channel we have noise that gets added. We have attenuation that happens to the signal. We've talked about what kinds of coding in these other boxes here. Source coding, right?
Correct.
Which was what?
Huffman coding.
Huffman or?
No.
Okay, yeah. Source coding is Huffman coding. Right? And then what was the other one?
Channel coding.
Channel coding. Hang on to that line coding answer for just 1 second. Okay, channel coding, and the example we used was what kind? Hamming, yeah. Hamming code. And Hamming code. Okay, so the other thing is this is compression. Compression, and this is redundancy for what purpose? Error correction. Okay, now those things both assumed we just had bits, right? We added bits for error correction and we removed bits. We lowered our average code length by Huffman coding. Problem is now we don't really have any method of matching this to a channel. We could say that our bits are represented by 0 and plus 5 volt levels, like TTL in a computer, but so far we have no real way to get it on the channel. So we're going to add one more block here, which is today's episode of stuff on the chart, and it's going to be line coding. That looks kind of like line cooling, but it's supposed to be line coding. All right.
Oh, really? This is political. This is political.
This is nice.
They changed characters? Oh, that was the worst.
Okay, couple things about line coding. First off, what is line coding? Anybody have any guesses?
Coding on the line.
Yeah, it's coding stuff so we can put it on the line, right? In general, up to this point, we've just treated stuff as bits, and we could go a step further and say that those bits now are represented by two voltage levels, like 0 and plus 5 volts. So far, so good. The only problem is we've got some issues with that. Number one, we've got our signal power. What do we want the signal power to be? Okay, we want to have maximum signal power, and if we use 0 and 5 volts, what's our average signal power? Assuming that zeros and ones are equally distributed.
3.5?
2.5 is the average voltage squared. Yeah. No, it's not RMS because these are square pulses.
2.5 squared.
So whatever 2.5 squared is, 16. No, 4. 8, what? Less than 9. Sorry, more than 4, less than 9. Yeah, 6.25. Okay. So 6.25 watts, but our maximum is what? What's our maximum power? 5 squared. So our maximum power is 25 watts, right? So our average is only 6.25, but we have to be able to handle a maximum of 25. What we would really like is for our maximum and average to be the same so that we're not wasting a lot of capacity, right? I'm like, right, everyone's like, we'll just wait and see how this turns out. We're not going to commit ourselves until we get farther along here. Okay, so signal power, there are two things. Physical signal power is how much physical power it takes to send it, and then there's logical signal power, which is the amount relative to the physical power that it takes to send a particular set of ones and zeros. Okay, next thing is the bandwidth required. We want that to be as high or low as possible. Which one? Right, we want the required bandwidth to be as low as possible, right? So that we can send as much as possible through a particular amount of bandwidth. Then we have to somehow detect, we have a threshold that we need to detect. So for example, if I'm using 0 and 5 volts, so a 0 is a 0, plus 5 volts is a 1, I have to have a threshold here at 2.7. It could be. Let's just, for the sake of argument, say 2.5 though. Somewhere in between. It doesn't actually matter exactly where. 2.5 is going to give us the best chance of noise not running us either way across the line. But we've already talked about attenuation. What happens when we receive this thing? Yeah, that 5 volts is going to be attenuated down to, I don't know, 1 volt maybe. So here's our threshold. So all we receive is zeros all the time. Oh, yeah, that sucks. Okay, so all we get is zeros, so that's kind of pointless. So let's just make our threshold 0.5 volts. But then if we like extend our cable a little bit and get more attenuation, then we have to change the threshold again. So now our threshold is dependent on the length of our run, which kind of sucks. We'd like the threshold to be independent of that and independent of the 0 to 1 ratio, and yeah, immune to attenuation, right?
That's what we like. That's not the
Okay, that's what we would like, and you're saying that's impossible? Could be. It is, given what we've got right now. So we're gonna now.
blackboards.
Yeah, it is impossible by using 0 and 5 volts for our 0 and 1, and that's the whole point of line coding. So now we have to come up with some sort of line code or some sort of representation that has these properties. Then the last thing is, does anybody know what a PLL is?
Phase lock.
You might. What's it? Okay, I got phase locked loop and what? This is the. I can't believe you guys haven't been. It's the Palestine Liberation Library. There's a whole bunch.
People be in front.
What? Okay, phase locked loop. It is phase locked loop. What is a phase locked loop? Does anybody know?
No.
It's used on the receiver end in order to
Okay.
actually capture
Yeah, it does.
Turn.
Okay, no, you're right though. It's a phase locked loop is a device used on the receiving end to keep the receiving clock in sync with the sending clock so that you don't get off and start picking up the wrong bits. We want to stay synchronized with the incoming bits so that we know we're not dropping any. Okay, so in order to refresh the phase locked loop, because of the way it's designed, it needs a 0 to 1 transition, a 1 to 0 transition to because it times itself by counting transitions, right? That's how it resets, keeps itself going. So in this case, if we had a 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 0, 0, we'd have 0, 1, 1, 1, 1, 1, 1, 0, 0. What would happen to the phase locked loop during all of this? It just kind of drift, right? There's nothing in there to tell which bit we're on. So you can think of it as refreshing the phase locked loop. Alternatively, just think about it as, I mean, even looking at the graph, it's hard to line that up with the ones below it, right? Because it's just a line.
So does the phase lock loop essentially act as like a flip-flop?
Yeah, phase lock loop, it's something like that. It's actually a higher frequency clock that then can adjust itself slightly to stay more or less in the center of the incoming bit. Okay. That's exactly what that's what we're going to talk about. So Manchester encoding is the way that we do this.
Because the Manchester drops, it changes in the middle.
Increases before it drops.
Yeah. Okay, so here we are. Speaking of which, we've got a couple of possibilities for doing this. Number one is called non-return to zero, and this can be unipolar or bipolar. It's sometimes in some textbooks called antipodal, but we're just going to call it bipolar. Okay, so non-return to zero, we've got a 1, so it goes up to 1, it goes back to 0, and it stays there. If it goes to 1, it stays there. Okay, so let's see if this fits any of our things that we said. Is this immune to attenuation if it's unipolar? So like if that's 0 and 5 volts, well, that's what we were just talking about here, was unipolar, 0 to 5 volts. How about if it's bipolar, -5 and +5 volts? Is it immune to attenuation? What's our threshold? Now we just need to be able to tell the difference between +5 and -5. So 0, right? Our threshold is 0. So if it attenuates, how does that change our threshold? It doesn't, right? It stays 0. So hey, making it bipolar has made it immune to attenuation. Does it refresh the phase lock loop if we have a long string of ones or zeros? No. Does it fix our power issue if we make it bipolar? We got plus 5 volts and minus 5 volts. So our average power is now... Nope. Nope. It's
voltage for 400.
Nope.
Is that not 20 volts?
No, it's not 20. It's,
Yeah,
yeah, you're getting there.
Tell us what it is or he's not.
Okay. All right. Yeah, it's 25 because it's either plus 5 squared, or it's minus 5 squared. But either way, it's 25 watts, right? Okay, so it stays constant. Our power stays constant, which is what we want. Okay, now let's look at return to zero. This can be done a couple ways. Return to zero means if we've got a 0, and this is the unipolar way. If it's 0, it goes to 1, it returns to 0 halfway through the... so you see this is only half as long as the one above. So it has a pulse that's half as long, so it returns to 0. At 0, it stays 0, and then for every 1, goes up, returns to 0, goes up, returns to 0. Okay, does this solve our threshold problem if it's unipolar? No. Nothing. We might as well just throw this out there right now. Nothing unipolar will ever solve the threshold problem. Like you said, it's impossible if 0 is one of your ends, right? The only way to do it is by having plus or minus. Now, the other thing is, what's our average power like? Well, let's say that this is, well, if it's bipolar, the average power is okay, right?
The unipolar from NRZ is a squared over 2, and polar is even more efficient with a squared over 4.
Right.
I want to be in notes from some.
Yeah, and we'll get to that here soon. Okay, but now here, how about our refreshing the phase lock loop? If we have a string of 1s, are we going to have transitions for our phase lock loop? Yeah. Hey, so we've improved on the NRZ, but what if we have a string of zeros? It'll just stay at 0, so that doesn't help us. It helps us somewhat, but not completely. So that brings up Manchester coding. Did you guys talk about this in math or someplace? In Cisco, you talked about Manchester? Okay. Manchester coding is slightly different. The level has nothing to do with the bit. It's the transition or the 0 crossing that represents a bit. So in this case, a 1 you can see is represented by a high to low transition. Then this 0 is represented by a low to high. We have to go back to 0, back down, because the next 0 is also represented by a low to high. Then this 1 is represented by a high to low. We go back up. The 1 is represented by a high to low. And then, well, presumably that looks like there's going to be another 1 coming up after that because we went back to high voltage. Okay, how about this? Is this going to provide transitions for our phase lock loop? Yep. Always. No matter what we get, the very worst case is if we get 1, 0, 1, 0, 1, and even that's going to have transitions every cycle. If there's strings of 1s or 0s, it provides 2 transitions a cycle, right? Or per bit. Okay, then the other one is BAMI. How many of you have heard of this before? Okay, BAMI was that stupid kid that they added to the Flintstones. No, wait, that was Bam Bam. Never mind. Not quite the same. Oh yeah, the alien was the stupid one. All right. At some point we'll have a little quiz question. Which was worse, the alien on Flintstones or Scrappy Doo? All right. Anyway. Okay, so BAMI is binary alternate mark inversion. So the way it works is a 0 is just a 0, and a 1 is what we call a mark. And the mark is either a positive or negative voltage. So in this case, what happens is the first time you hit a 1, you go positive. That's a mark. Then, and this is called a space. So you have a mark or a space. A mark, space, space, mark. Now, since it's alternate mark, the mark has to be negative. Then the next time, the mark has to be positive, and so forth. So, okay, so you still have, if we have a string of zeros, it's the same as RZ, right?
So when would you not use Manchester?
Yeah, we're going to end up using Manchester most of the time, but these are different line codes that get used. All right. Okay, so if we look at this, the signal power, RZ has the same power as NRZ, but antipodal or bipolar is much greater signal power than unipolar. You can figure the signal power is the average power of each value of 0 and 1. So like bipolar, the average power is 25 if we're using 5 volts, right? Because it's plus and minus 5 volts. Unipolar, the average power is the average of 0 watts and 25 watts. So average power is 12.5 watts. So bipolar is much, much greater than unipolar. Bandwidth, it's the same whether it's bipolar or unipolar. Return to 0 needs more bandwidth than non-return to 0. Does that make sense here? Looking at this, here's NRZ versus RZ, you notice that this has to change more often, so it's going to use more bandwidth. And then return to 0 has an intersymbol buffer. Do you guys know what guard bands are?
No, maybe we should discuss it.
That's what. Yeah, that's when you see the MPs. They have this band. Oh wait, no, that's not a guard band. What's a guard band?
Just the buffer between two bands so that you don't get the bleed over.
Okay, right. For example, if you're tuning up and down your commercial FM dial, what are the 2 closest adjacent stations that you can tune to?
1 megahertz?
They're odd numbers.
Right, odd tenths of a megahertz, right? So there you have one at like 99.7, and the next possible one would be 99.9. Okay, so you have 200 megahertz separation between adjacent stations. In practice, the bandwidth required for an FM station is 100 megahertz. So what that means is, since there's 200 megahertz separation between 2 adjacent ones, we've got plus and minus 50 megahertz surrounding each of those. Then we've got a 50 megahertz guard band that's theoretically dead frequencies between those 2, right? What about guard bands in space? Is that possible? I mean, I don't mean in space. I mean spatial guard bands. What's that? Can we separate? Okay, what we're doing when we talk about guard bands in frequency, we're talking about separating a separate dead space in frequency between 2 things. Well, let's do the next easier step first. What about in time? Can we have guard bands in time?
I would think so. You just stop transmitting.
Yeah, you just stop for a minute
Okay.
before you. Yeah,
Like pulse
right.
transmission.
What's that?
You pulse the transmission.
Right. Okay. And so then you don't get 2 time separated like TDMA things over the top of each other because you have a little bit of a gap between them. Okay, what about spatial guard bands? Is that something that would be possible?
Geographically separated signals are.
All right.
I mean, you have 100.7 in Cleveland and 100.7 in Atlanta. They're not going to interfere with each other.
Okay, that's exactly right. Yeah, we can reuse the same frequency over and over as long as they're geographically separated. And there are, if you read through all the FCC stuff, there are, based on transmit power level and so forth, there are minimum distances where they'll allow a new license to be issued for that same frequency because they're setting up spatial guard bands, right? Okay, so here, return to 0 has this ISI buffer in that you're not going to confuse two adjacent pulses because there's a separation. There's always a separation between them. Whereas here, they just run right into each other. So it takes more bandwidth, but we do have a little buffer. Now, the threshold, if we do bipolar, our threshold can just be 0, right? But if we do unipolar, our threshold we set to be V over 2. We said 0 and 5 volts, it would have to be V over 2 at 2.5 volts. Can that be constant? Well, no, because with different length we have different amounts of attenuation, so we have to keep adjusting it up and down based on the length we are away. And then finally for refresh, antipodal is the same as unipolar, but return to 0 is much better than NRZ, and Manchester is better than either one. Yeah.
I don't know if this is me, but the polarization.
Yes, I know. Sorry. I actually meant to fix that last night, and I just forgot.
Because I'm noticing on other sides, and there's a lot for those of us with a marginal graph, we struggle when we see that to know whether or not it's a bullet or if you're,
Or a minus sign. Yeah, I know. I will fix that from here on out. Yeah. Good. Okay.
You mind discussing for a minute more about why return to 0 needs more bandwidth than non-return to 0?
Oh, okay. Sure. Taking a look at this here, think about the fact that think of this as just being a wave, right? Wave here. Can you see that this is a lower frequency wave than this? Right? So the general point is bandwidth is used up by more changes and transitions. Anytime you have a change or a transition, that increases the amount of bandwidth you're using.
I thought we're just talking about using a couple frequencies, right? Or the same frequency?
No, this is all the same frequency. This right now we're just talking about, we haven't got to using a couple frequencies. We will talk about that later. In which case, we can't really say NRZ versus RZ because we're just using two different frequencies or two different phases or something like that to represent the 2 bits. In this case, it's if we were trying to send this actual waveform, right, then the more transitions we have, the more bandwidth it's going to take up because remember the steep corners are higher frequency. And so the more transitions we have, the more it takes. Right, and particularly if you just kind of think of these as being sine waves, this is a lower frequency wave than this thing. Right?
This is between 1 and 1. You got to do like 3 changes.
Right. Yeah, you just have to do more.
Really one change.
Exactly. Here you have to do changes every time. Here you just have the 1 if you have a string of 1s. Does that make more sense?
In return to 0, the pulses used to delineate change are shorter than they are in not return to 0.
Right.
So then wouldn't that indicate the difference in bandwidth if the pulses are shorter?
No, the pulses are shorter actually makes it use more bandwidth, right? Because in the same amount of time we have to have more changes in the waveform. Now you're right though. If you start thinking about this, and this is why we usually just don't send things like this, right? When we transmit it, we usually use QAM or FDMA or TDMA or CDMA or one of these other multiplexing methods that we'll talk about later. But this is just the basics of line coding. And then we'll talk about better ways to do it a little bit later. Okay, so last thing, Manchester code is a transition. A 1 is a transition from 1 to 0. A 0 is a transition from 0 to 1. There are implementations of Manchester where that's opposite.
Just depending if you're reading the trailing edge or reading.
Yeah. Okay, the bandwidth is greater than return to 0. Why is that? If we're talking about transitions, increased number of transitions mean higher bandwidth.
For the NRZ, it only did it for ones. For Manchester,
It's got to do it zeros and ones.
So it's doing a change every time.
Right. So more transitions. The threshold, if it's unipolar, then it's V over 2. Again, we don't like doing that because we don't want to mess with the threshold when attenuation happens. So let's make it bipolar or antipodal. And yes, Major McCreary, I see that this does look like minus equals 0, which doesn't make much sense. So I'll fix the bullets. It's independent of the 0 to 1 ratio, which is nice, and it's by far the best for a phase lock loop because there's always a transition on every bit, and sometimes 2 transitions per bit. Make sense? Big problem with it is that if we have 1, 1, 1, 1, well, let's draw that out. And then we'll do this really quick and then take a break. Okay, so 1, 1, 1, 1, 1, 1. We've got 1 is a transition from 1 to 0, right? And then we've got to go back up to have the next transition from 1 to 0, next transition from 1 to 0, next transition, next transition, and next transition, right? Okay, now, so that's the waveform for 1, 1, 1, 1, 1. So let's say that we just we picked this up partway through. We're like, okay, well, let's see. Oh, that must be good. Okay, so that's 0, 0, 0, 0, 0, right? Because every transition from low to high is a 0. So if we screw up on the phase by half a cycle, it looks exactly like all zeros. So in general, we have to initialize it with 1, 0, 1, 0, 1, 0, which means we've got 1, 0, 1, 0, 1, 0. So 1, no transition, 1, no transition, 1, 0. So what's the advantage of doing that? Yeah, the only place we have a transition is on the ones that we're supposed to be checking. So now we're not going to accidentally get onto this middle one like we did up there. So we initialize it with that, and then hopefully the phase lock loop keeps it good enough that it doesn't slip.
But Hamming code also, correct?
Well, the Hamming code doesn't do anything for it because the Hamming code just determines the pattern of the bits we're going to get in there.
Yeah.
But we always have to have this, a 1, 0, 1, 0, 1, 0 kind of initialization in order to get it started. And then the Hamming code, there are going to be 1s and 0s in some random order. Okay. What about doing this in fiber? Well, I mean, okay, we've seen already it works great for, what's that? It works great if we have bipolar. So what we do is we send a burst of light for a 1 and a burst of dark or negative light for a 0. We send anti-light down there for a 0. Okay, suddenly everything's different, right? Now we can't do bipolar things with light because the government is keeping the dark bulb under wraps. I mean, that would totally revolutionize lighting, but they don't want to let it loose. It's like the car that runs on water. They're just keeping it quiet. Yeah.
We can measure like what the brightness is at one voltage and compare it to brightness at a lower voltage.
Yeah, you can have intensity differences in a fiber, but even so, then now you've got to, if you've got attenuation, that brightness is going to lower, and so you have the same problems as with unipolar. So Manchester, not as useful for optical stuff, right? Okay, let's come back after break and talk about differential Manchester, which